Hello everyone. In this presentation, I'm going to walk through high-level dose characterization for commercially available Landauer nanodet OSLD. It will be kind of follow-up work to my master thesis. The roadmap of this presentation will be like this, starting with the motivation, and then step by step, I will try to introduce you what I did, how I did, and what I have in terms of results. And in the conclusion part, we will discuss what is the difference between low dose assessment, which is my thesis, master thesis, and what is the difference between this low dose and the high dose. What is the motivation of this work? Why I did this one? There are many nuclear sources all around the world, including the current capabilities and the future works. In terms of current capabilities, there are more than 400 nuclear power plants. 50 are under construction, meaning that at least 10% increase in number of nuclear power plants. Moreover, we have advanced reactors, which is more economical, more reachable, even transportable. So we have adding some nuclear materials to current capabilities. And space applications are also one way to use nuclear technology. So with the current capabilities in terms of nuclear warheads, it is around more than 10,000. So these are, if we sum all of these, we get more and more nuclear materials. These are all related with the safety, security, and safeguard, 3S in the nuclear industry. Safety focuses on protecting environment and people. Security is focused on protecting the nuclear materials itself. The safeguard is the mechanism that counts each nuclear material and to be sure that each of them are in use in a peaceful way. So to do that, for the special security and safeguard application, we have currently have a mechanism, methods like using radiation pagers, portal monitors, isotope identification systems, and radioactive imaging system. In my master thesis, I suggested that the micro Landauer nanodet OSLDs are capable an alternative method to detect any illicit nuclear material activities. With this framework, first, for the low dose, I go and get the background dose, initial dose, and the bleaching constant for low dose, that microstar reader. Then put a framework like this. Think that you are putting the OSLD on a corridor, and in that corridor, you know what the radioactive source, what the nuclear source can be with the given geometry. Assuming this geometry for a given nuclear facility with this formula, we I did be able to distinguish from the background dose that I obtained from the low dose assessment with the dose from this shielded spent wheel assembly, and it worked. In this work, what is the difference? Difference is instead of using low dose, now I am using the high dose. So each nanodot that I have used during this experiment exposed around 500 milligram dose. So it's kind of realistic case. So in this case, we did the experiment as same as the low dose assessment. So we have no replacement case and the replacement case. In the no replacement case, basically I take the nanodot OSLDs, put to the reader, read it 30 times and change it, put a new one and do the same thing. In the replacement case, I take the OSLDs, put into the reader, read just one times, get it back, take the new one, read just one times, do it 30 times simultaneously. So, as I explained in my master thesis, the way that we do is, why we do this, because the none of the OSLDs you use in this framework may be read out for more than one facility, more than one authority like NRC or like International Atomic Energy Agency. So they can prefer their own methods. The goal is to check and see that is there any statistical significant difference between these ones. In the low dose, we checked and see that there is no statistical significant difference. So it's time to check the high dose part. So how I did the measurement, like I mentioned, and got the Bleaching constant and the initial dose, and applied the analysis of variance to see that is there any statistical significant difference between the measurement when you change the measurement type. So the dose is calculated by using this formula. The microstar basically do LED for LED exposure measurement of the dosimeter and then take the mathematical average of the expected dose. The expected dose in here in the unit of milligray. So D is the dose, C is the average row counts, B is corrected background, and the calibration factor is the factor that using the average row counts, it will turn to the dose in units of milligray. It's converting it. So sensitivity adjustment factor and the sensitivity. Each parameter in here have its own uncertainty. And if we apply the first order uncertainty propagation to this formula, we can get this formula here. The difference between the low dose and the high dose assessment is the calibration factor, which is different here. But other than that, all the uncertain parameters are same with the low dose assessment as in my thesis. Again, we know that these C, S, these parameters are not independent, but it's a really good approximation to neglect these three of them. This is the dominant one. But to be consistent, I put all the variables here. And then when we are done with the experiment, we can apply the analysis of variance to see that is there any statistical significant difference in the Bleaching constant? Is there any statistical significance in the initial dose estimation? For the ANOVA, we have some definition like factor, treatments, and observation. In our case, Bleaching constant, for example, is a factor. Measurement type like all replacement and no replacement is the treatment, and the results we get are the observations. So what I have, let's discuss the results. The results will be discussed in two steps, in experimental results and then the statistical analysis of that experimental results. Starting with the experimental results, we need to put a function to fit the data, to model the data. In this case, it is different from the low dose assessment. Here, the initial dose is really high compared to background dose, so the suggested function in the low dose assessment case will not work in this case because the background dose is so small when compared to the high dose. So my approximation to data is this function, which is including the Bleaching constant, initial dose, and the number of reads. For the all measurement set, the function worked well, and we got the data related with, you can see here, M1 and M2. And the blue holes are the data, and the red line is the fit that with the suggested function. It also worked with the no replacement case and the replacement case. So it's time to analyze the results in terms of statistics. So starting with the Bleaching constant. We have Bleaching constant with its own uncertainty, and let's put all the values on a box plot. So this is the box plot. In the box plot, we can see that the variance is supposed to be different, but we need to check it. When we check it, we see that the variants are heterogeneous, so we can't use the classical ANOVA. We can use Welch ANOVA, and the Welch ANOVA suggests that there is no statistical significant difference in Bleaching constant. By the way, the Bleaching constant is a parameter that depends on the reader and represents how much dose equivalent light is removed with each readout. So we need to check the ANOVA assumptions here, and we see that the residues are approximately normal. One thing to be considered is the variants are not homogeneous according to the Bartlett test. The same thing will be done with the initial dose. We see that the initial dose and the uncertainty for each case and we are taking all of them and putting on to the box plot. And with this case, we see that the variants are homogeneous. And the so we use the classical ANOVA. Classical ANOVA suggests that there is no statistical significant difference in the initial dose, and the initial dose is the average dose representing the value before any readout. So again, diagnostic says that the residues are approximately normal, which is the NO assumption, and the Bartlett test suggests that variants are homogeneous in this case. So as a conclusion, we observed there is no statistically significant difference in different kind of measurements. So the framework is still working well. And in the previous work, in my thesis, different measurement types did not significantly affect the low dose accumulation. So one can conclude that the Landauer microstar dosimetry system, either way of doing measurement is acceptable for both low and high doses. Now I obtained the bleaching constant and the initial dose. What is the difference between high dose and low dose? One thing is bleaching constant for high dose is approximately one of 10 of the bleaching constant for the low dose. And the other distinguishable difference in the value of bleaching constant, the bleaching constant statistical behavior for both cases is the same. The errors are normally distributed with the mean zero, and the variance are heterogeneous. But the statistical behavior for the initial dose is different for the low dose and the high dose scenarios. Although we check that the errors are normally distributed with the mean zero, variance are heterogeneous in the low dose assessment, homogeneous in the high dose assessment. So with this reference, I am done. Thank you for your attention. I look forward to hearing your question.